This example looks quite a bit like the previous example, but it has a complication. In this system, we know the value of x in terms of z, but then we know the value of y, not in terms of z, but in terms of x. So we have a z here and an x here, and they're different. Which means that if we replace x by 2z and y by x minus 5, we'll still have two different variables in our equation, which is not what we want. Instead of that, we'll do our substitutions one at a time. To decide what order to do them in, we notice that the one variable that appears in all three equations is x. Since x appears in all three equations, we'll do the substitution where we replace x last. We'll do the substitution where we replace y first. So our first step is going to be to plug equation 2 into equation 3. That'll give us 2x minus 3, y is equal to x minus 5, plus z equals 9. So I'm going to go ahead and simplify this because it'll make my future life easier. 2x minus 3x plus 15 plus z equals 9. Let's see, I'm going to combine these like terms, and I'm going to subtract 15 from both sides. I've got negative x plus z equals negative 6. And I'll call this equation 4, because it's a new equation in multiple unknowns. So I've used equation 2 and 3, combined those to get 4. 1 and 4 now involve x and z. I can directly plug 1 into 4, which will give me negative x is 2z plus z is negative 6. Oh, well, that's actually pretty easy, right? Because that'll be combining like terms. Negative z is negative 6. Z is 6. I've got one of my variables. Now I can go back and get the values of the other two. I have z, so equation 1 will easily give me x. I'll have x is 2z, so 2 times 6, x is 12. And now that I have x, equation 2 will easily give me y. Y is x minus 5, so y is 7. I'm going to check that in 3. Right, I'm not going to make a mistake at this step or this step, but I might have made a mistake earlier. So 2x, x is 12, minus 3y, y is 7, plus z, z is 6. Does that equal 9? Well, this will be 24 minus 21 is 3, plus 6 is 9. Yes. Again, you can just plug that in on your calculator if you'd like. Our solution then is x is 12, y is 7, and z is 6. This system was set up to make substitution easy, but we had to do it in 2 rounds because x and y were given in terms of different variables. We chose the order that we did for the rounds because we wanted to replace the variable that occurs in all three equations last. Okay, let's see another example, which is more confusing than difficult. This is another example of a system that's set up to make substitution easy. However, looking at it, at first we don't spot that this is a system of three equations and three variables. Each equation here only contains two variables, but the entire system does include all three of x, y, and z. The entire system does include three variables. What should we do with this? Well, the answer to that question is we can kind of do whatever we want, but we have to pick something. We can do our substitution in any order we like, but we have to pick an order and just do that. So I'm going to leave 3 alone as long as possible because it's got that fractional coefficient in it. I'm going to start by plugging 1 into 2. So I'm going to replace this y by this expression that's equal to y. I'll have z equals 2 times y is 1 minus 2x minus 8. So simplifying that, z is 2 minus 4x minus 8. Combining like terms, z is negative 4x minus 6. Well, that's a new equation. I'll call that equation 4, but it's not immediately obvious that that helped me. Why not? Well, because I've gone from having 2 equations with 2 variables each to now I have another equation with 2 variables. Why is that good? Well, we notice that equation 3 and equation 4 have the same variables. So equation 4 here has the same variables as equation 3. So equations 3 and 4 now form a system in x and z. And I can plug, it looks like either one of those into the other. I think my fraction-related life will be easier if I plug 3 into 4. So I'm going to replace x in equation 4 by that expression that's equal to x. I'll have z equals negative 4 times 1/3 z minus 5 minus 6. I'll distribute. Z equals negative 4/3 z plus 20 minus 6. Now I'll add 4/3 z to both sides and combine the 20 and the negative 6. I've got 7/3 z equals 14. Divide both sides by 7/3, and I'll get z equals 6. Okay. Now I have the value of z. It looks like equation 3 is going to be my easiest way to plug in z and get something else. I'm going to use 3 to get x. So x is going to be 1/3 times 6 minus 5. 1/3 times 6 is 2, minus 5 is negative 3. So my x is negative 3. Looking at 1 and 2, it looks like 1 is going to be the easier way to get y. Then I'll have y is 1 minus 2 times negative 3. and that'll work out to 7. So I've used 3 and 1 to get my remaining variables. I need to check in 2. And I'll have z is 6 equals 2 times y is 7 minus 8. Is that true? 6 is 14 minus 8. Yes, that's true. So my solution is -3, 7, 6. Again, this was well set up for substitution. I just had to pick somewhere to start. And in this case, I could have picked anywhere I liked to start. I picked what I did because it looked like it might make the arithmetic easiest.